Let's go over some basic definitions again. And these are some slightly formalized definitions as opposed to the usual operational definitions we work from. First of all, a vector can be considered a physical quantity of a mathematical construct that represents a size, called the magnitude, and a direction. A scalar is a physical quantity or mathematical construct that represents a size or magnitude only. We are all familiar with vectors, whether we understand the term or whether we are new to the term. Examples of scalars and vectors. Scalars, you can have things such as mass, because it really doesn't make much sense to think about 3 kilograms west. Speed and distance are things that are scalars, but we oftentimes don't realize that we're talking about only the magnitude as opposed to the vector form, which are velocity and displacement respectively. Another example of a vector is weight. It's the force. That's a common mistake you see on packaging where it says net weight and then gives it to you in kilograms. Pounds measure force, kilograms measure mass. Formalized definition for vector addition. Essentially, if you have two vectors, A and B, then what you're looking at for the sum of A and B are simply the sum of the constituents or the components in the I direction or the X direction, and so on with the J and K. We can talk about higher dimensional vectors, mathematically and physically. That is a topic. It's just not one we usually cover in this course. So if we have a large brown delivery truck that travels 9 blocks north, 12 blocks west, and 5 blocks south, what is the final displacement from the point of origin if all the blocks are the same size? So using our common definitions and comparing those to a compass rose, north would tend to be a positive, east would be a positive, south and west would be negatives. So we could say that we have 9J plus 12I, and that's west, so it would be a negative, and then 5 said that all wrong. Let's try that again. All right, if it's 9 blocks north, that would be 9J, and I wrote an I a minute ago and did it again. West would be a negative 12I. South would be a negative 5J. And so if we're adding these, we can consider the resultant to be 9 and a negative 5 would be 4J. And typically we list them in order, IJK. So we can think of our resultant as a negative 12I plus 4J. Now graphically, we could do this. It is a little bit cumbersome, but it comes out to be something like a 9 arrow going that way, and then a 12 length arrow that way, and then a 5 length arrow that way, so that the resultant would look something like this. A boat is capable of traveling in still water at 1.45 meters per second. It must cross a 350-meter wide river and land downstream 155 meters. If the boat must travel at 35 degrees, determine the river current. Probably should be a comma there, but anyhow. So what we need to do is we need to find out how the boat needs to move. Now, if it has to move at 35 degrees, there's some reason, some parameter that must travel. What this says is that the velocity is 1.45 meters per second, and the angle is 35 degrees. This results in components of 0.832 and 1.4 let's see, 88 meters per second. So what we now know is we can determine the amount of time that it takes to move horizontally. If it's a distance of 350 meters and we are able to move at 1.188 meters per second, then horizontally, our displacement, our distance, which is just speed times time, is 350 meters. Our speed is 1.188 meters per second. So our time that's better, is approximately 291.6 seconds. So if it takes 291.6 seconds to travel 350 meters, it's going like this. It's going to take the same amount of time to travel 150 meters downstream. Now we don't know what the current is. I'm going to say vertically. That's simply based on my drawing. It's really a downstream direction. All right. So it's the speed of the current plus the speed of the boat that equals the total speed. Well, I don't know the current. I'm going to leave that as V sub C. The boat, I was able to determine at the top, 0.832 meters per second. And that is my total speed. Distance times time, again, just like I did. So we move 155. Let me write that down. Speed times time. So we move 155 meters with a total speed that we don't know yet in 291.6 seconds. So that means that our total speed is going to be about 5.32 meters per second. Since the current is 0.832 times the 0.832 plus the total, excuse me, since the current plus 0.832 is the total, we know that the current is equal to the total minus 0.832. So that means the current in this case is 0.532 minus 0.832. So that gives us a current of a negative 0.30. And if we look at the number of significant digits, we have 2 in our horizontal distance. We have 3 in this downstream or vertical distance. So we would only use 2 meters per second. Since that's a negative, that tells us that in fact, while I drew it going up, it would go this way.